Okay, so it wants you to find the density, or it says the density of the atmospheric air varies with elevation, decreasing with altitude. Okay, and we want to obtain a relation for the variation of density with elevation, and then calculate the density at the elevation at 7,000 meters. Then it says calculate the mass. All right, so I'm going to help you do both, help you set up both. Okay, so here is the Earth. And this dotted line is the outer part of the atmosphere. So the Earth, actually the radius is what's given. So the kind of the ground level is 6,377. Then it goes out to 6,402. Is that right? For the beginning and end? Yep. This is problem 5, yes. So those are actually radiuses or radii. I'm not sure which one's correct. Radii. So this is 6,377 all the way down to 6,402. So z is the, if you want to think of it as the elevation or altitude. So at this number, this is 0. In the bottom one, it goes all the way down to 25. Yeah, radius. So the numbers are given as radius. Then it says, well, that z is elevation. That actually is, it's kind of written wrong, but it goes from 0 to 25 because what's 6,402 minus 6,377? That should be 25, right? Yep. And the density, 1.225 all the way to 0.04008. Is that right? 0.04008. All right, so how do we find, what was this? Obtain a relation for the variation of density with elevation. So what does that mean? Find a relationship. Anytime you hear that, what do you think you got to find? Huh? A graph, or in the result, you'll end up getting an equation of that line. Yes. So I want you to plot density versus z. I think you'll get something like this. And in Excel or in MATLAB, you can fit, and you just fit a second order. It's fine. 1.225. So does that seem okay? So you fit second order. A, B, and C are your constants that you'll end up getting. And then the other question, it said find the density at 7,000 meters, right? Or is it 7 kilometers? Yeah, so 7,000 meters. So how would you do that? What? Yeah, just plug in, yeah. So just plug in here, 7 kilometers. And here. And you should get it, I don't know, it should be somewhere. Oh, thank you. It should be somewhere in this region, right? Because this is 25 kilometers. So it better be within your range of table values. It shouldn't be off your table values. So that's a good way to check. So that's part A. Okay, now part B, that's the tricky part. So the density changes as we go up, right? So if we want to find the mass of something, typically the density is always the same, right, in that chunk. So how do you find it if you know the volume? So this is let's kind of look at this, and it's kind of like notes. So we know the density is mass over volume, so therefore mass is density times volume, right? But because the density changes, anybody want to guess what we do? Integrate. Yes, yes. So what we do is, in order to find something, we integrate over its volume. Right? Because say we had, if the density was constant, what could we do with the density in this equation? Comes out of the integral, right? And then we just have the integration of a volume. If it's a cube, we just integrate like 3x, y, and z, and we end up getting the length times width times height, okay? So this is the fundamentals that we have to do. We have to integrate. So we need to figure out what dV is. Because we know the density, right? The density is az squared plus bz plus c. So let's take a little adventure here, and we're going to take a step back. Let's take a circle. And we want to find the area of this circle. So the way we can do this in calculus is we take a strip, a really small strip around this, and we'll call it a change in R. Okay? It's really, really tiny. All right? We can call it a really, really small change in area. And we could do that a whole bunch of times and add them up. Okay, and we add them all up, that's like the integral. Okay? If we take this strip and we make it long, we stretch it out. This is still a small change. And anybody want to kind of tell me what we can use for this length? Yeah, which is what? I think it's 2 pi r, right? Or pi d, 2 pi r. So in calculus, the change in area, the small amount of area, is actually, we just multiply these two together. So we get 2 pi r dr. How do we find the area now? What did I say that we had to do? Sum them all up or take the integral? So can someone take the integral of 2 pi r dr? So 2 pi r squared over 2, and look, pi r squared. Holy smokes. We just derived how to find the area of a circle using calculus. So that's the area. We kind of do the same thing for volume. We're almost done here. So if we take a cube, oh sorry, could be anything, doesn't really matter. So the black little cube is a really small infinitesimal amount of volume. And in order to find the total volume, we'd have to have all those filled up, right, inside the red box. And we'd add them all up, and that's the volume. Or we integrate x times y times this small change in dx, or dz, sorry. What is x times y? It could be an area, right? So this is really what we call a surface area. Anybody know what the surface area of a sphere is? Because if we're looking at the Earth, now it's a sphere. So for a sphere, yeah, 4 pi r squared. Yeah. For the surface area. So for a sphere, in order to integrate this, to get the total volume of a sphere, you would integrate that, and what would you get? 4/3 pi r cubed, right? Or dv is 4 pi r squared dr. If we just do the differential. All right, and the last step, and then you can leave, is now the mass we said was rho dv, and we could just plug in what we had. And try this. And I'm going to substitute z for r. And now you have what it takes to solve the last part of that equation.